Now let's look at the basic equations for fluid statics, also called the barometric equation. dP by dZ, the change in pressure by elevation, is equal to negative rho density times G, which is also equal to negative G MP over RT. And that comes from few slides back. So we can rewrite that as dP by P is equal to negative Gm over RT by dZ, just by getting the P to the other side. Sorry, I just missed on a slide. Wanted to use the pen. So getting this P here to the other side, and then getting the dZ to this side. So where Z is the vertical distance and G is the acceleration due to gravity. If T and M did not change with elevation, the temperature and the mass, so we could integrate this to find the relation between pressure and elevation. The changes in mass are not important, but those of temperatures are, as we just talked about. This explains why a hot air balloon can go up and can go down based on its temperature. So a parcel of air does work on its surroundings as it expands. So now that we are heating some air, it expands, it makes some work on its surrounding parcels. It exchanges negligible amount of heat with its surrounding, thus it undergoes a reversible adiabatic process. Here, the balloon serves only to isolate a parcel of air for our consideration. So the main idea of having the balloon itself is just to make sure that we have a parcel inside and a parcel outside. If we can separate them by any other mean, this should also work. So the balloon expands as it rises and thus does work on its surrounding. Accordion-pleated balloon requires no work to stretch. Heat transfer between balloon and surrounding is not zero, but it's slow enough to be ignored. From this, we will talk about something called the isentropic process, where a parcel of air moving upward without significant mixing with the air around it, reversible adiabatic behavior, which is also called isentropic process, would be observed. And in this case, we're saying that the dP over P is equal to Cp over R dt by T, where Cp is the heat capacity of the gas at constant pressure. So we can write that, the previous equation, dt by dz at adiabatic perfect gas is equal to negative Gm by Cp. This is always applicable on Earth. It's also true on Mars and Venus. In some planets where they have storms constantly, that equation does not hold. However, it holds whenever you have calm vertical movement. dt by dz is equal to negative Gm over Cp. This will get us to the next concept, which is called the lapse rate. Now, the lapse rate is the change in temperature per elevation, dt by dz. Remember the equation over here? Sorry, just get the highlighter. This equation here, dt by dz is equal to negative Gm over Cp. Now, this equation describes the change in temperature by elevation. So when we go up, how the temperature will change. If we go on top of Jabal Hafid, how the temperature will change, or if we go underground, how the temperature will change. So we can write it as dt by dz is equal to negative Gm over Cp, and we can substitute. G is 9.81, M is 29, CP is 3.5 times R, which so 3.5 times 8.314, and just divide by 1,000 to make the units. This is equivalent to -0.00978 Kelvin per meter, which is almost equal to 10 degrees Celsius for every kilometer. So what does that mean? That means that whenever we're going up 1 kilometer, the temperature should drop by 10 Celsius or 5.4 Fahrenheit for every 1,000 feet. This is the theoretical amount. We call this lapse rate. Lapse rate. How is the change in temperature with elevation? So we can see it here. This is in the curve, this is the dotted line over here. This is the adiabatic atmosphere, where it goes down if this is between the temperature and the height. So the temperature is decreasing every 1 kilometer by 10 degrees. So if now the lapse rate, the actual lapse rate, is more than 10, for example, 12, if it changes 12 degrees Celsius for every kilometer, we call this super adiabatic lapse rate. If the actual lapse rate is less than 10, we call that sub-adiabatic lapse rate. So now we have two important concepts. If it's more than 12, then it's super adiabatic. If it is less than, more than 10, then it's super adiabatic. If it's less than 10, it's sub-adiabatic. Now, let me show you on this graph what the super adiabatic means, meaning that if we start at the same here, we will go less than 10. So a super adiabatic will look something like that. So it will have less slope than your adiabatic atmosphere. Now the other one, the less adiabatic, the sub-adiabatic, will look something like that. So let me just use it with a different color. So this would be, the blue one will be your sub-adiabatic, while the green one will be your super adiabatic. Another curve is something called standard atmosphere. So, but what happens in reality? If we take all the averages, all the observations, day, night, summer, winter, everything, they did it in the USA, and they averaged it for a very big period. They came up with a new concept, something called the standard atmosphere. Standard atmosphere. Now, the standard atmosphere lapse rate is 6.49 Celsius per kilometer, also equal to 3.56 Fahrenheit for every 1,000 feet. Now we can see that this is almost about 66% of the adiabatic lapse rate. The standard atmosphere is 66% from the adiabatic. So why, on average, don't we have the theoretical assumptions? Because the adiabatic assumption is really not appropriate for all circumstances, or even the average of all circumstances. In the next video, we'll explain why is a difference between the standard and the standard atmosphere and the adiabatic atmosphere. So before you move to the next video, just if you don't understand what lapse rate, what is adiabatic atmosphere, what is super adiabatic or sub-adiabatic, please don't move to the next video. Watch this again, try to understand that before moving to the next video, because the next video will just say to start building on that.